Recording is rolling. It is Wednesday, October 30. We're going to continue on these textbook puzzles. Guys, remember yesterday we did chapter 8?
Yeah.
Right. Guys, whatever we did from chapter 8, as long as you wrote that down, I'll pick that up. When? Guys, when am I picking these up? Friday. Right. So tomorrow I think I'm going to do a lab with guys and get you guys the next take-home quiz. I'll pick these up by Friday. But just whatever we do in class today, we'll just do that. All right. So that'll be able to do. All right, so chapter 9, gravity questions. Here's universal law of gravitation. I guess I got it twice. Oops, there it is. F equals gmm over r squared. Number 33, calculate the force of Earth's gravity on a 1 kilogram mass. Hey, I have one of those right here. Boom, there's 1 kilogram. Here's the mass of the Earth. Here's the radius of the Earth. Does the result surprise you? Well, let's see how surprised we're about to be. Number 33. You guys know force equals G M M over R squared. Right? There's universal law of gravitation. All right, well, you guys are writing that down. Here it is. So there's the poster for that, right? You guys got that? All right. All right, then F. Okay, well, F could be the force. That could be the weight. So I guess we're solid for that. Except to solve for. G. Hey, is that the universal gravity constant? That's like this number right here. Okay, can I see that number? Let's do that. 6.67 times 10 to the negative 11. And the units go Newton meter squared per kilogram squared. Okay, there's your G. Mass of the Earth. What do they call it? 6 times 10 to the 24 kilograms. Usually I use like 5.97 or 5.98, but they're going 6. So let's use their number, 6. That's 10 to the 24 kilograms. Then little m, well, that could be this guy right here, 1 kilogram. 1 kg. Feeds in right there. Okay. And then divided by, the distance between this object and the Earth is the radius of the Earth. Same thing for each one of us sitting in this room. Okay. So let's use the radius of the Earth. They said 6.4. I usually use 6.38. They said 6.4. And that's 10 to the 6 meters. So millions of meters. So there's one more thing I got to write. Guys, what am I forgetting? Squared. Right there. Okay. Gotta square the R. All right. All right. You guys see that? Look, there was no algebra at all. It's just arithmetic. All you have to do is just plug it in. So can you plug it in? You guys got calculator. You guys got calculator. So let's see. Can you correctly plug that into the calculator? That's the next test. Right, everybody sees why this formula, where each of these numbers is coming from. Right, mass of the Earth, radius of the Earth. Right. Can you correctly plug this in? Right. So open parenthesis, 6.67 times 10 to the power negative 11. Close parenthesis. Open. This model calculator automatically multiplies, so that's nice. 6 times 10 to the 24. Close open. 1 for 1 kilogram. Close. Divide by. Open a parenthesis. 6.4 times 10 to the 6. Close parenthesis squared. Right. Here. Before I hit enter, give you guys a moment to catch up. And you guys tell me, I think you should probably know at this point in the class what the answer is before I even hit enter. But yeah, what's that? How do you put what? Like this meters unit. You don't. Like this. Yeah. You don't. You just type the number, right? So guys, the calculator just does the math part with the numbers. When I write all the units out, that's the extra physics part. You don't actually put the units in the calculator, right? Just the numbers. Right? Like when I hit enter, it's going to be implied that there's units attached to whatever number shows up on the screen, but the calculator just does the numbers part. Okay? We got to attach the units ourselves. Right? Oh, because when I hit enter, what number should I get pretty close to? 9.8. 9.8? Should get 9.8? You guys think? Yeah, I should. And guys, what should the unit be? 9.8 what? Newtons. Let's see if it actually is. 9.77. That is 9.8 newtons, isn't it? All right. Right. So the second question was, does the answer surprise you? Well, I guess it doesn't surprise Gabe. Is anybody else surprised? I hope not, because that's exactly what it should be. Oh yeah. Ooh, calculate the force of gravity on the same mass if it were one Earth radius above Earth's surface. So if you double the distance, actually, I kind of have a picture for that. We dig through these posters here. Here we go. Guys, this one right here. You guys remember this one? Okay. You guys see this guy standing on this tower that's as tall as Earth's radius? Right? No, that's just in my picture. There's no building that's actually that tall, but it's good. Right. Guys, if you're twice as far away from the center, twice as far away, what's the gravity field? It's how many times as much? Sure. If you throw a factor of 2 in that r, what's 1 divided by 2 squared? Is that like a quarter? Right? Half of a half is a quarter? You guys see that's this point exactly on the graph? If you're twice the distance from the center right here, you guys see you're getting like a quarter of the gravity field, therefore a fourth of the gravity force. Right? So guys, what's a quarter of 10? Like 2.5?
Yeah.
And this is a little bit less than that, so maybe somewhere between 2.4, 2.5, something like that. Right. Let's see that. So that's the next question, number 34. All we're gonna do is make that one change. Actually, can I fit that down here? I think I can fit that down here. 34. F new equals. Okay, I got the same 6.67 times 10 to the negative 11. Right. I got the same mass of Earth. 6 times 10 to the 24. I got the same 1 kilogram mass. This is all going to come out to some number of newtons, so I'll just pull the unit out here. Right. But now, guys, this radial distance. Guys, how should this be different than before? Guys, if you're standing on top of a tower that's as tall as the Earth's radius, aren't you double the distance from the center of the Earth compared to before?
Yeah.
Can I just say 2 times this? So 2 times 6.4 times 10 to the 6. And then, well, meters, but I pulled that out. No, this is all being squared again. Okay. So there, I pulled the unit out newtons. Okay. All right, everybody good?
I'm chilling.
All right. So you're working with your pencil, right? Not cutting it. Oh yeah.
Plus between 6.4 and
That's multiply. That's multiply. Guys, the mass of the Earth. That's scientific notation. Does. Oh, down here. That's a multiply. Yeah. So 2 times 6.4 times 10 to the 6. All right. Let's put it all here. So actually, you know what? Here, guys, watch this calculator trick. Because you guys plugged this in and got 9.77 newtons, right? Scroll up. Hey, there's that calculation. Scroll over to the right. Scroll. Right. Until you get to this bit right here. 6.4 times 10 to the 6, which is right here. Scroll over the 6 and do second insert. Do you guys see second insert right here? Second insert. 2 times. That's it. Now you have your new formula. Boom. Save you a little time, right? Nice little calculator tricks. Right. Now, again, let's see if you guys are following. When I hit enter, what number should pop up on my screen?
9.8. 2.45.
About 2.4 or 2.5, somewhere there. Guys, this is what we've been saying. If you back up to twice the distance from the Earth, you should have a quarter of the gravity force. A quarter of 10 is like 2.5. It's a little bit less than that. Let's see exactly what do I get. Oh yeah, 2.44 newtons. Guess it's like a quarter, right? All right, everybody good with that? All right, what's next? Let's do these two. Because 35, 36. These kind of go together, sort of. Oh yeah.
Can I get a band-aid?
Yeah.
Oh, yeah.
All right, so calculate the force of gravity that the Earth pulls on the moon. Okay, so the Earth pulling on the moon. And then number 36 says calculate the force of between Earth and the sun. Ooh, hey, guys, take a guess. Which force do you think is bigger? The moon pulling the Earth or the sun pulling the Earth?
Sun.
You guys are saying the sun?
They're equal.
Let's find out. Let's find out. You might be right.
That might
The
be-
moon- Let's do a show of hands. Guys, show of hands. Which force is bigger? Here, I'll draw a picture. Here's the Earth. Here's the moon. Here's the sun. This is not to scale, but you guys get the sun's bigger, but it's further away. The moon is smaller, but it's closer. Right? There's a gravitational force between the Earth and the sun. There's a gravitational force between the Earth and the moon. Which force is bigger? So your options are either the Earth moon force, the sun moon force, or do you think they're equal? I guess that could possibly be, right? So show of hands. How do you think the Earth moon force is bigger? Who thinks that's a bigger force? Who thinks Earth sun is bigger? Who thinks they're the same? All right, well, let's find out. So we're gonna start with all right, so we got votes on each one of those. All right, each one's get some votes. All right. Earth. All right, so we're starting with Earth moon. Earth moon right here. Let's do force Earth moon equals. You guys ready to do force Earth moon? You guys know F equals G M M over R squared. We're just gonna play off that. All right. So 6.67 times 10 to the negative 11. Here, I'll pull all my units out. Let's just do some number of newtons out here. Okay. Mass of the Earth. What do they say for mass of the Earth? What's their number? 6 times 10 to the 24. That's kilograms. The mass of the moon is 7.4 times 10 to the 22 kilograms. All right, guys, pause right here. You guys see 6 versus 7? Guys, 6 and 7 are almost the same number, right? Right. So let's just compare the order of magnitude. 10 to the 24 compared to 10 to the 22. Guys, this is saying the Earth is about how many times as massive as the moon? What's 10 to the 24 compared to 10 to the 22? Guys, if you write 1 followed by 24 zeros, 1 followed by 22 zeros, how many zeros different is that?
2.
2. 100. That's it. Right? Guys, the Earth is almost 100 times the mass of the moon. You guys see that? That's a little side question. All right. Well, let's go back to this though. The distance is 3.8 times 10 to the 8 meters. I left off meters. Okay, that's being squared because I pulled all my units out here, just embedded it in the newtons. All right. So you guys see where all those numbers are coming from? All right. Notice it said average distance because the orbit is slightly elliptical. We'll take an average. All right. So open parenthesis. All right, you guys see if you guys can plug this correctly into the calculator, and we'll all get the same number, hopefully. 6.67 times 10 to the power negative 11, close open. 6 times 10 to the 24, close open. 7.4 times 10 to the power 22, close divide by open. 3.8 times 10 to the 8, all right, that's meters, right, close square. All right. I want to make sure because I haven't checked ahead of time, so I'm going to get a number, but I want you guys to tell me that I'm doing this correctly. All right. So I'm getting this number, 1.87 times 10 to the 23, and it would be newtons. Right. So if I did 187,000,000, just like a whole string of zeros, it's a crazy big number. It's like 10 to the 23 newtons. Right. Right. Here's the force from the Earth to the moon. Now, are you guys also getting the same number? Make sure I didn't do a typo there. You guys getting the same number?
I'll give your pencil back. Not bad. I think it was. What about this one? Nothing.
Maybe I have a typo. Let me see. Oh, yeah. I think you got it right. Let's see what you got. Okay. 2 times 10 to 20. Yeah, I do have a typo. Scratch this. This is wrong. Right. I see it right here. I didn't do 6.67. I did 6067. Oops. Let's do a point right there. Right. All right. Yeah, now we got the same thing. I saw Chloe get. You guys actually getting this number, hopefully. So let me rewrite this. 2.05 times 10 to the 20. Okay, and that's still newtons. Force, Earth, Moon. So, okay. All right. Now I think we're all getting the same number. So 10 to the 20 newtons. You guys getting 10 to the 20 newtons? Right.
I got 21. 21.
Sick. Oh. Where is it? 23rd.
You saw that too, didn't you?
Into the. Okay, it's right here. You did 10 to the 23rd. It should have been 10 to the 22nd. All right. All right. All right. Now you guys ready to calculate Earth to the sun? Earth, sun? All right, I think I fit that in right down here. So force Earth sun equals, it's going to be a ratio. You got GMM over R squared. Let's do G, 6.67 times 10 to the negative 11. M, no, mass of the sun. Oops, I need the mass of the sun. This is for 36. Guys, we're doing 36. What is the mass of the sun? It's 2, you guys see 2 times 10 to the 30 kilograms? Okay. A lot of times I'll call it 1.99 times 10 to the 30 kilograms. But let's use theirs. 2 times 10 to the 30. Now that's kilograms. I'll just take all my units out here just like I did before. Call it. It's going to be some number of newtons at the end of the day. Okay. Then mass of the Earth is, now that's what's orbiting. So that's back to 6 times 10 to the 24. That's kilograms for Earth. Okay. And then the distance from the Earth to the sun, 1.5 times 10 to the 11 meters. That's like 150 times 10 to the 9 meters, which is 150 billion meters. And that's being squared. Okay, 150 billion meters squared. So force from the Earth to the sun is, we're about to get a number. It goes right here. Right. Okay. You guys calculate it. I'll calculate it. Make sure I don't do a typo again. 6.67 times 10 to the negative 11. 2 times 10 to the 30. 6 times 10 to the 24. Then divide by, and then in parentheses, 1.5 times 10 to the 11, and then close parentheses, square that. All right, guys ready? All right. Because remember, before we set up equations to start solving, I asked you guys, I said, which force is bigger? The Earth to the moon or the Earth to the sun? I had you guys raise your hands, and I got answers for any of the possibilities. Is this bigger? Is that bigger? Are they the same? I got votes on each of those. We're about to find out right here. I'm getting 3.56 times 10 to the 22, and that's newtons. Are you guys getting the same number I'm getting? You guys getting that also? All right, let me make sure. All right, here, I'll double check my work while you guys are 6, 10, 11, James 10, 30s, 24. I'll divide it by 5, 10, 11 squared. Yeah, I think that's right.
Got it. Error.
Okay, let's see what you got.
Yes, Squidward had the brown. Squidward's a brown man. Yeah. But they're really not it. Yeah. Or. You don't like Squidward's house. That's really powerful. Oh, yeah.
All right. So, guys, to bring us full circle, which force is bigger, the Earth and the Moon, or the Earth to the Sun? The Earth to the Sun by a factor of about a what? How many times bigger is the force from the Earth to the Sun? Huh? Guys, what's 10 to the 22 compared to 10 to the 20?
100 times.
100 times. That's 2 decimal places. That's 100 times. right? Actually, it's even more than that because 3 is more than 2. So the Earth to the Sun, that's more than 100 times the force from the Earth to the Moon. Ooh, that's kind of cool. All right, what else we got? Let's see.
No.
Let's do 43. Let's skip down to 43. You guys see 43? Let's skip down a little bit. Many people mistakenly believe that astronauts who orbit Earth are quote unquote above gravity. You guys see that? Right. Guys, you guys seen astronauts in the International Space Station? They just floating around, right? But before I read the rest of this is number 43. Right. Let me draw you guys a picture. Guys, if this is the Earth, guys, focus here. Focus here. You guys write this down in your notes? Here's the Earth. Here could be a satellite, for example, International Space Station. It's going around Earth. It's really not that far above Earth in terms of like proportional to the radius of the Earth. Here's the radius of the Earth. Here's the radius of the orbiting satellite. Proportionally, they're not that different. Okay. So what do you think the gravity field is up here at satellite level compared to at the surface? Is it less than 9.8 meters per second squared? Yeah. Is it a lot less than 9.8 meters per second squared? Probably not. That's sort of the premise of this question here. It says calculate the gravity field for space shuttle territory 200 kilometers above the surface of Earth. Here's Earth's mass, here's Earth's radius. And then, there's a follow-up question. What percentage of 9.8 meters per second squared is that? This is a really good question. Really good question. Let's do this. So gravity field, that's like G-M on R squared. Is that true? Like that? Let's do this for satellite territory. Equals. All right, set up a ratio, the giant fraction bar. Let's do G is 6.67 times 10 to the negative 11. Right, in a bunch of units. Here, guys, I'll pull my units out to the side. What if I pull all my units out? There's crazy units here, there's kilograms here, there's meters here, and it's being squared. If I pull it all out, that's ultimately going to give me what unit for gravity field? Is what unit describes gravity field? Meters per second squared?
Yeah.
Right, meters per second squared. Is that true? All right, so pull my units out. The mass of Earth, that's what's being orbited. They say, here, I want to use their number. Did they say 6 times 10 to the 24? 6 times 10 to the 24. Right. Now that's kilograms, so I don't have to convert it. That's good. A lot of times I'll write like 5.98, but that's okay. All right, then now R, guys, they're talking about not the actual radius of the Earth, but the orbital radius, which is a tiny bit bigger. How much bigger? Well, let's put this in parentheses. We're going to add it. It isn't true that the orbital radius, little r, is the radius of the Earth plus the height of the satellite. Call it h. Is that true? Here, I'm going to write that. The orbital radius, lowercase r, is the radius of Earth, capital fixed capital R, plus the height above the surface. Is that true? Right. I'm going to substitute that right here. So let's do radius of the Earth. They said use, well, 6.38 times 10 to the 6. Now that's meters, but again, I pulled my units out already. So you guys know that's some number of meters, right? Plus the height above the Earth. And they said low Earth orbit might be, what number do they call it? 200 kilometers up, right? 200 kilometers up, right? So guys, what number should I write right here? Guys, 200 kilometers. How many meters is that?
200,000.
200,000 meters, right? 200 kilometers is 200,000 meters. Guys, is 1 kilo 1,000 of something? Right? That's a times up. Right? Guys, one more thing. I forgot one detail. What did I forget? Squared. Go square that. Okay. Makes it. All right. We're about to get gravity field for the satellite. I know this has to be less than 9.8 meters per second squared, but I'm not expecting it to be crazy less than. I'm gonna make a guess. Wait, yeah, what's that?
I got 9.243.
Oh, all right. Jake already got it. Got like 9.2 something. That sounds about right. That sounds about right. Let's see. All right, yeah, nice fast calculation there. 6.67 times 10 to the negative 11. Close open. 6 times 10 to the 24. Close divide by, and then open maybe some more parentheses. 6.38 times 10 to the 6. Plus an additional 200,000. Close
What?
square.
Good question.
All right. What's that?
9.24.
What's the question?
No, they were asking right now.
Oh, let's see if I get the same thing. I should. Yeah, there it is. All right, 9.24. That's meters per second squared. Yeah, that is a little bit less than the surface level of the gravity field, isn't it? Yeah. Okay.
No.
Yeah.
It's like attached to a rope or string.
24. 6.38.
But that's not.
U plus.
Oh.
He's hypnotized.
Let's see if that does it.
Yeah.
All right. You guys good? You guys
Yeah.
good? Yeah. So the gravity field is nearly the same as what it is on Earth. It's just that they're in perpetual free fall. They're always falling around the Earth. Yeah. That's 43. Okay. Now there was a follow-up question to 43. Let's call it 43A. 43B is saying what percentage of the surface gravity is that? So I'll say ratio equals, let's go 9.24 meters per second squared compared to 9.8 meters per second squared down at the surface. This is still 43. It's just an extension question. Guys, 43 says so calculate G for space shuttle territory, which we just did. We got 9.24 meters per second squared. But there's another question that says, your answer is what percentage of 9.8 meters per second squared? So it's still 43. Okay. So we're trying to do that right now. So all I have to do is take the ratio. Say, here's what it is up in shuttle territory. Here's what it is down at the surface. What's that ratio?
0.94.
That sounds about right. That's about right. Yeah. All right, I'm getting what Jake got. You guys getting that too?
Yeah.
0.94. Right. Now, as a percentage, what is that as a percentage? 94%. 94%. Right. Now, that's really low Earth orbit. That's probably as low as you can be, just barely above the atmosphere. Low Earth orbit extends a little bit above that too. So a lot of times I'll just round this down to about 90%. Say like you have 90% of the gravity field up there that you do down here at the surface of Earth. Kind of where that is. All right. All right. So you guys go with gravity field. Gravity field. All right. Let's do
36, 39, or 40.
no, if I'm skipping them, don't worry about them. Unless you really want to do them. Okay? But I'm trying to be a little selective here. I like this next question. 52. Let's do 52. What would the path of the moon be if somehow all the gravity just vanished to zero? So I'll try you guys some pictures and you guys tell me what the right one is. So 52. Here's the Earth. Here's the M for moon. Okay? E for Earth, M for moon. Here's the moon, go around the Earth.
I wonder why.
All right. So you guys good so far? Right. Let's do a free body diagram on the moon. Guys, what force is acting on the moon? Yeah, gravitational force from Earth. I'll call it F sub G. Right. If you think back to a few questions ago, I'm leaving off a big part of the story. Because which force do you think is actually way bigger? The moon to the Earth or the moon to the sun?
Moon to the sun.
Moon to the sun. That is true. It should be about 100 times bigger, shouldn't it? Right? This is a little side thought, right? But if you're just focused on the Earth moon system, then this is all that's going on from the point of view of the moon. Right? Right. Now, the moon has an instantaneous velocity this way. Is that true?
Yeah.
Right. So if you're wheeling this around, let's find a different neat color here. Ooh, I got green and gold. Here. Boom. School colors. If gravity suddenly switched off. Boom, right there. Would the moon, option A, fly off in this gold direction here? Or would it, option B, fly off in this green direction right here?
B.
Guys, let me see, show of hands. Show of hands. Guys, everybody look up here. Guys, everybody look up here. Here's the moon going around the earth. Suddenly, here comes the moon. You suddenly turn it off gravity. Boom. Who thinks the moon makes a 90-degree turn and flies straight away? Who says that? Who says that? Who says the earth the moon follows this green path right here? Yeah, that's it. Check, bing. Say tangent to its path. All right, so you guys get on 52? All right. See, what else we got? Yeah. So you guys know the moon would follow a path, tangent to its motion, right? It's the green one. The moon goes this way. This is not anything.
What if it's the red? What if it's the red?
No, it's just that there.
That says E and Earth, the black. ink.
Yeah, E is Earth.
I know, but what if it's the black? ink? Is that the right answer?
Huh? Okay. Guys, here's a similar question. You got a tennis ball on a string, and you're winding that in a circle. Hey, up in a helicopter, I'm looking straight down. Here's you. You're playing. You're wheeling this around your head. You guys see the tennis ball going. Right, and then you let go of the tennis ball. Guys, everybody look up here. Which way does the tennis ball fly off? Does the tennis ball fly straight away from you?
No.
Or does it fly off tangent to its path? Tangent to its path. It's gonna go that way. If you let go of the string right there, tennis ball goes that way. Okay? Same thing. Which law of motion is that called? Newton's first law of motion. Oh yeah. Law of inertia. Let's do here, guys. Let's do one more, and then I'll play a video for you guys. Number 47. Here's the last one we'll do. This is going to finish all the puzzles. In fact, if you want to turn these in by the end of the class, you'll be able to after you do number 47. 47. But you guys got to pay attention here. Pretend you fall into a hole, bored completely through the earth, just like this picture. Guys, everybody look up here. Fall through the earth. Discounting friction, rotational effects. There's no air drag. It's nothing like that. Or that. Rank from greatest to least. ABCD. You guys see those points ABCD for your speed and your acceleration. So we're going to rank these, and this will be the last one we do. And this is all I'm going to grade, is everything we've done. And then number 47 is going to be the last one I'm going to grade. Okay. So let's do speeds. I'll get 4 speeds lined up. V for speed. I'll get 4 accelerations lined up. A for acceleration. Let's just say which way from greatest to least. Okay, so inequality signs. Inequality. All right, you guys got that? Okay, everybody got that all set up? All right. All we need to do to finish this off is to rank these with subscripts. Okay, I need some A, B, C, and D going on. Okay, are you guys ready for that? All right, let's start with speed because that's one I got first. All right, so guys, which one of these? Where do you? Okay, so you were at the surface here at the top, and you fall through. But like Alice in Wonderland, you're falling down this hole. Maybe.
What's your favorite movie, like Disney movie?
Well, right now it's Alice in Wonderland. It's the only one I can think of. Guys, where do you think the speed is the greatest?
B. No,
B. Yeah. Because guys, all the time you're falling towards the center, there is a net force towards the center. You're going faster. After you pass B, you're going to whiz by B really fast. Then you're kind of falling upward, aren't you? Just towards the opposite side of the earth. You're going slower. Right? In fact, by the time you get to point D, how fast are you moving?
0.
That's this one here. Is 0. Right? Now let's compare A and C.
No.
Well, okay, if you somehow could, simplification, here's what would happen. Is you'd have 0 speed at the surface.
If you don't die.
Guys, focus here. You have zero speed at the surface. As you fall faster, faster, faster. Now, what's your gravity force right at the center?
Zero.
Zero. Zero right at the center.
So you float for the
Right.
like.
Now that doesn't mean you're not moving. That just means you're no longer accelerating. Right? But you are moving really fast. So you're gonna whiz past that point. And after that, you slow down, slow down, slow down, slow down. And then when you reach the other surface on the other side, you go to exactly 0 meters per second.
Is it possible or just a score?
Well, nobody's kind of been able to physically do that. That'd be a really, really hard thing to do.
But like if we have the material sooner,
Would it be possible? Okay. Here's a crazy question. Is it physically possible to drill all the way to Earth's core? Probably not with today's technology.
But like
Maybe 1,000 years from now. But yeah, you have to have some imagination for that though. All right. Hey guys, look at A compared to C. Guys, focus here, focus here, focus here. Do you guys see A and C are the same distance from the center? Right, so you're speeding up as you get to A, and then when we cross C, you're slowing down. But is it the same speed, do you think, A and C?
Yeah.
Right, I'm gonna say equal. I'm gonna change this inequality to an equal sign. I'm gonna put A and C as the same. Okay. Right. Now maybe we really should have done acceleration first because acceleration is proportional to the force. In fact, if I put the forces, they would be the exact same answer as the accelerations. Okay. So, guys, where do you, let's start with point B. Guys, point B, what is your net force again? 0. Therefore, what is the acceleration? 0. So this is point B, which is equal to 0. Okay. Right. How about guys, where's the greatest force? Guys, which of these points is the greatest force? D. Right? We're at the surface where all of Earth's weight's pulling you down. Therefore, that would be also the greatest acceleration. Okay. Now, A and C, are those at the same elevation type?
Yeah.
So do you think they're the same force and therefore the same acceleration again? Changes to equals A and C. Okay. All right, you guys get that?
Yeah.
All right. And more importantly, like why that would be. That makes sense, right? So if you're at the surface, you got all Earth's weight pulling you down. That's the greatest force, and therefore the greatest acceleration. F equals ma. That's Newton's second law of motion. As you fall down into the center of Earth, there's less and less gravity pull, so less and less acceleration. Although you are going faster and faster as you go towards the center, you're going to zoom through the center as fast as you'll ever go, and you slow down going towards the opposite side of the Earth. Okay, that's it. All right, we're gonna hang those up right there. I got an asteroid video for you guys.